Alright guys, today we're going to start the chemistry chapter, which is chapter 2 for Anatomy and Physiology 1. Now I start every chapter with a list of objectives. These are things that should guide your studying while you're initially learning the chapter and until I give you guys the study guide. Again, continued objectives to guide your studying as you work your way through the chapter. Alright, so this chapter is on chemistry. Real quick, I do want to let you guys know that this is one chapter, so 3 lectures, that covers a huge amount of information. We cover topics from General Chemistry 1, General Chemistry 2, Introductory Chemistry. We're even going to cover topics from Organic Chemistry. So, if you take those classes, that's like 5 semesters worth of classes. We're cramming that information into 3 lectures. So what we're doing is a very surfacey overview of chemistry. And the reason for that is there are some very important concepts that you guys have to understand in order to understand the body and the way that cells work and the way that our tissues work. So if you've taken chemistry before, when we go over some of these concepts, it might seem like we're not getting into all of the details, and we're not getting into all the details. We're just kind of, again, going over the surfacey concepts, and we're really targeting the things that are going to apply to the human body in some way. So if it doesn't apply to the human body, we're really going to kind of leave it alone. We're not going to go there. You can cover all of those topics in depth by taking chemistry itself as a class, okay? Also, just a warning, if you have not taken chemistry before, or if it's been a really long time since you've taken chemistry, this might seem a little odd. It might be kind of difficult to begin with, but I beg you, just bear with me. When we talk about these concepts, I'll introduce them, and then we'll go through multiple examples until you feel comfortable with the information. So again, just bear with me, keep working through the examples, and hopefully, after a little bit, it'll click. If not, shoot me an email or post a comment and you can ask your questions and I'll see if I can explain it in a different way. All right, that's it. We'll start out with just a few definitions related to chemistry. And the first of these is matter. So matter is defined as anything that takes up space or has mass. Mass is kind of like weight. So anything that has weight or size that takes up space in the world, no matter how small that space is, it can be microscopic, absolutely itty bitty tiny. If it takes up space or has any size to it, it's matter. Based on that definition, absolutely everything you've ever seen or touched is matter, right? You are matter. You take up space, right? This water that I'm drinking, the water is matter. The cup is matter. The air that I'm breathing is matter, right? It's made up of oxygen atoms that are very, very small, but they're still there, right? They still take up some space. Absolutely everything, the table, the computer, all of it is matter. So everything all around us, including our bodies and everything in our body, is considered matter. So this matter is made up of billions and billions and billions of atoms. An atom is the smallest stable unit of matter. An atom is like one single unit of something. So say we were talking about oxygen. One single oxygen. Okay, again, we're talking so small. Microscopic doesn't even do this justice. It's so tiny. But one individual oxygen is one atom of oxygen. Or carbon. Okay, one atom of carbon. One single unit of carbon. Sodium, right? One single sodium is one atom of sodium. Now, again, these are very, very small. So we're saying that us, right, our body is made up of atoms, but atoms are tiny. So how is it that we get to this big, huge human body, right? Or not huge, but we get to this big human body. Well, those atoms join together to make bigger things. Okay, so for example, hydrogen, two hydrogen atoms join together with one oxygen atom, right? That gives us H2O, which is water. So tiny atoms join together and they build something bigger. Now, everything in the world is made out of a limited number of atoms, right? Different types of atoms. But when those atoms join together, they can make new chemicals that have completely different characteristics. And that's how we get this variability in our body, right? Like we have all different, we've got water, we have our skin cells, we have our hair, we have our muscle cells, we've got all these different types of chemicals and structures. Because as the atoms join together, again, they can make new chemicals that have new characteristics. Again, let's talk about water. So water, we said, is H2O, two hydrogen atoms and one oxygen atom. If I have just hydrogen atoms, okay, at room temperature, I have just hydrogen, that's actually a gas, right? Like the air around us, right? A gas. If I have just oxygen atoms, that's also a gas. So I'm taking hydrogen gas and oxygen gas, putting them together, and I get H2O, which is a liquid at room temperature. So these atoms, because I joined them together, they're now forming something that behaves completely differently than the original atoms. Okay? And we can do this, we can combine atoms in all sorts of different ways to give us all different types of compounds, like fats or sugars or proteins. Now, the chemical characteristics of the atom are important, like the size of the atom, the charge of the atom. This is important because it's going to determine the physiology, or like the behavior of the molecule. The way that the molecule behaves in our body is going to be based off of its chemical characteristics. And this ultimately is why we care, right? This is anatomy and physiology. Why do you care about the chemistry? Because the chemistry determines the way it behaves in our body. So our body is considered matter, right? We take up space, we have some weight or mass, and our body, right, the matter, our body is made up of atoms, billions and billions of atoms. Each atom has a specific structure. Okay, atoms are made of what we call subatomic particles. There are 3 different subatomic particles that can come together to form an atom. Those subatomic particles are the proton, the neutron, and the electron. Okay, proton, neutron, and electron. Atoms can have all different combinations of these, right? Maybe they have 2 protons and 2 neutrons and 2 electrons. Or maybe they have 2 protons and 1 neutron and 2 electrons. When we look at the atoms, atoms are structured like you see in this picture over here on the right. In the very middle of the atom, there's a dense, heavy part of the atom called the nucleus. So there in the very, very middle is the heavy, dense nucleus. And then we have these little shells or clouds where we have electrons orbiting around the nucleus in what we call the electron cloud. So a dense, heavy nucleus in the core of the atom, and then an electron cloud, which is essentially an orbit that the electrons move around in. Okay, so let's talk about the characteristics of these subatomic particles. Again, every atom is made out of some combination of protons, neutrons, and electrons. Protons are in the nucleus of the atom, okay, so they're in that dense, heavy core of the atom. Every proton has a positive charge. So you can match up the P's, right? Protons are positive. So that means if the atom has 5 protons, it has 5 positive charges. Every proton also contributes to the mass of the atom. Again, you can think of mass like its weight, right? The weight of the atom. So again, if the atom has 5 protons, that contributes 5 mass units to the size of the atom. Neutrons are also in the nucleus of the atom. Okay, so if you look here at the nucleus, notice it has these little white dots which represent neutrons and these little red dots which are representing protons. So the nucleus is made out of the protons and neutrons. Neutrons are neutral. Okay, neutral means no charge. Okay, so they're not positive, they're not negative. Okay, they have no charge, hence they're called neutral. But they do have some weight, they do have size to them. Every neutron gives 1 mass unit to the weight of the atom. So if it has 5 neutrons, that gives another 5 mass units to the overall size of the atom. Finally, we have electrons. Electrons are not in the nucleus. They're orbiting around, right? Really, really fast, moving around in the electron cloud. Again, think of the electron cloud like this space or this orbiting area that goes around the nucleus, okay, around the outside of the atom. So electrons are constantly orbiting, right? Moving all around in that electron cloud. Electrons have a negative charge, so opposite of the proton. Protons positive, electrons negative. So if an atom has 5 electrons, it has 5 negative charges. Now, electrons are tiny. They have a very, very, very low mass. Their weight is so incredibly small that we don't even consider it when we're looking at the weight of the atom. So if I have an atom and I'm trying to figure out, how much does it weigh overall, I'm not even going to look at the electrons. Okay, it's negligible. They're so tiny, it just doesn't matter. You can think of it like if I have a pool of water, right? I have this big pool of water, and I know how many gallons of water I put in that pool. Okay, say the pool is 10,000 gallons of water, right? And then I add 1 drop, right? 1 more drop of water. Does that matter? Is that going to change the amount of water in the pool? You're not going to say 10,000 gallons and 1 drop, right? The drop doesn't matter because there's so much more water than that. That's kind of like the weight of the electron to the atom. The atom weighs so much more than that electron that it just doesn't matter. You could have another electron or you could have 1 less electrons and it's not going to change the size of the atom at all. Okay, so looking at this, we have kind of some information here that we can kind of sum up. First off, you know that atoms are made out of protons, neutrons, and electrons. You know that the protons and neutrons are in the nucleus of the atom, right? The dense core in the middle of the atom. And you know that the electrons are moving around, right? Orbiting around the atom in the electron cloud. When we look at an atom, there are a couple major things that we look at. One, we look at the charge. What's the overall charge of the atom? So in order to get the overall charge of the atom, you would do the number of protons minus the number of electrons. Protons are positively charged, electrons are negatively charged. That's why you subtract the number of electrons. So if they're the same, right, if you have 5 protons and 5 electrons, they cancel each other out and the atom is neutral. The atom has no charge overall. If you have 5 protons and 4 electrons, 5 minus 4 is 1, right, positive 1. So the atom would have an overall charge of positive 1. Okay. Neutrons, notice, are not in there at all because they're neutral. They just don't matter for charge. Now, if we're looking at the mass of the atom, like the size of the atom, how big is it, then the two things that we're going to look at are the protons and neutrons. Remember, electrons are small. We don't care when we're looking at mass. So mass is the number of protons plus the number of neutrons. In a little bit, when we talk about bonds, we'll see a few examples of this, but you should be really comfortable with this. If I say you have an atom and it has 6 protons, 5 neutrons, and 6 electrons, you should be able to tell me its overall charge, you should be able to tell me its mass, etc. Well, again, we'll go through examples in a little bit. Okay, so we know that everything around us, including us, is matter, and that all of us, our body, everything around us, it's all made up of atoms, lots and lots of atoms. So an element is the most basic chemical that we have, right? It's a pure substance. A pure substance that has only one type of atom. We have what's called the periodic table of the elements. I'm sure you've seen the periodic table before in school. The periodic table lists all of the known elements for us. So, and those are just pure substances. They cannot be broken down into simpler substances. They're in their most basic form already. For example, hydrogen. Right? Hydrogen is an element. Lithium is an element. Oops, Na is the symbol. That's why I'm writing Na. Na is the symbol, but Na is the symbol for sodium. Okay, sodium is an element. Carbon, the symbol for that is C. Carbon, you don't have to memorize the symbols, you guys. Carbon is an element. Okay, these are basic, pure substances that cannot be broken down any further. Now, you could have a bunch of oxygen, so I could have like 1 million atoms of oxygen, but if they're all oxygen, then that is a pure element. That's a pure substance, okay? Now, an element is determined by its atomic number. When you look at the periodic table, for example, right? When you look at the periodic table, you'll see a symbol in the middle. Okay, that's the symbol for H is a symbol for hydrogen. So the symbol for the element is in the middle. Then there's a number. That number is its atomic number. Every element has its own atomic number. So 1, atomic number 1, that is the atomic number for hydrogen. That identifies hydrogen, nothing else. The atomic number 1 does not give you any other element. It is hydrogen. That's it. 3 is the atomic number for the element lithium. The atomic number of 3 literally defines lithium. It doesn't go with any other element, just lithium. Now, this atomic number gives us very important information about that element, or all atoms of the element. The atomic number tells you the number of protons in each atom of that element. Okay, so that might sound kind of confusing, but all that means is I said hydrogen has an atomic number of 1. That means all hydrogen atoms have 1 proton. That rule doesn't change. If it does not have 1 proton, it is not hydrogen. Okay, if it has 2 protons, you're not looking at hydrogen. That happens to be helium. But all hydrogen has an atomic number of 1, which tells you all atoms of hydrogen have 1 proton. Okay, so again, hydrogen, atomic number 1, all hydrogen has 1 proton. Carbon, okay, carbon is atomic number 6. All carbon atoms have 6 protons. Okay, that never changes. In a little bit, we'll see that there can be different numbers of neutrons, or we can, have more or less electrons, but the number of protons never changes. Okay, the number of protons defines the element. So carbon, every carbon atom has 6 protons, period. Now, when we look at the periodic table, hey, I said that you have your little square and it has the symbol, so H for hydrogen. It has the atomic number up top. Under the symbol, it has the atomic mass. So for hydrogen, the atomic mass is 1.00794. 1.00794. I think that's correct. That is telling you the average mass for all hydrogen atoms. So like the average size for all hydrogen atoms that exist. Okay, so we're going to talk more about the mass here on this slide. So we know that the periodic table lists all of the elements, all of the pure substances. We know that there's an atomic number for each element, and that tells you the number of protons that all of those atoms are going to have. And then we know that underneath there's a mass, and that mass tells you the average mass for all of that atom. So for example, all of that element. Hydrogen. The atomic mass for hydrogen is 1.00794. That means if I took all hydrogen in the world, right, and I averaged all of the weight together, this is the average weight. It's pretty close to 1, right? So that means that most hydrogen in the world is going to weigh 1 mass unit. That is very small. Hydrogen's the smallest element. Okay, so most hydrogen weighs 1 mass unit. But notice that this is not an even number, right? It has this 0.00794. That means there must be some hydrogen that weighs more than 1, right? So there are different versions of hydrogen. Those different versions of hydrogen are called isotopes. So an isotope is a different version of an element that has a different mass number. So it's a different version of the element that weighs a little bit different, right? It might be a little bit heavier or it might be a little bit lighter, but it has a different weight, different isotopes. Now, remember that we said the mass, right? The mass, the size of the atom is the number of protons plus the number of neutrons. Now, if I have say I have 2 hydrogen here. I have this hydrogen that weighs 1 mass unit, and I have this hydrogen that weighs 2 mass units. Now, remember we said hydrogen, so that's going to be protons plus neutrons, right? So over on this side, protons plus neutrons is going to equal 1. Over on this side, protons plus neutrons is going to equal 2. Now, we already know that hydrogen is atomic number 1. That means that every atom has 1 proton. And remember, the number of protons does not change, period, or it's not hydrogen. So in both of these, right, the hydrogen that weighs 1 mass unit and in the hydrogen that weighs 2 mass units, both of them have to have 1 proton. That doesn't change. So if one of these is a little bit heavier, it's not because it has more protons. It must be because it has more neutrons. And that is exactly what is different about different isotopes. Different versions of the element are heavier or lighter because they have a different number of neutrons. Again, the number of protons does not change. So the number of neutrons must be what's different. So if I tell you that I have 2 isotopes of carbon, and I say, what's different between these 2 carbon atoms? You could say they have a different mass, right? They have a different weight. And you could say they have a different number of neutrons, right? That's why the weight is different, because they have a different number of neutrons. Again, the atomic mass on the periodic table is not a whole number because it's showing the average mass of all isotopes, right? So all versions of the element that exist on this Earth, average their mass all together, that's what you get. So here I'm just showing you the different isotopes of hydrogen, right? Or again, I could say the different versions of hydrogen. So this here, this first picture is showing us most hydrogen. This is what hydrogen typically looks like. It's hydrogen 1, right? Its mass number is 1, meaning it weighs 1 mass unit. Remember, hydrogen is atomic number 1, so that tells us it has 1 proton, and that's not going to change. So here in the nucleus, you can see that 1 positively charged proton. And remember, mass equals the number of protons plus the number of neutrons. So if the mass equals 1 equals, and the number of protons is 1, okay, 1 equals 1 plus 0. There must be 0 neutrons in order for it to weigh 1 mass unit. Now, I will tell you guys real quick, before the atoms have reacted or done anything crazy in their original state, they are overall neutral. So they have no charge overall in their base state. That means that the number of protons must equal the number of electrons, right? Because remember, charge equals protons minus electrons. So if we want them to be neutral, that means we want the charge to be 0. So if we want the charge to be 0, protons must equal electrons. So in this basic state here, we said this hydrogen has 1 proton, which is positive. That means it must also have 1 electron, which is negative. So that this little E that you see out here with the negative, that's the electron floating around in that electron cloud, right? The positive proton and the negative electron cancel each other out so that it's neutral. That's most hydrogen. Now, if you were to start gathering hydrogen from the world, eventually you would come across hydrogen that's a little bit heavier. This is hydrogen with a mass number of 2. Now, hydrogen with a mass number of 2, right? So if the mass is 2, 2 equals protons plus neutrons. It has hydrogen, so it must have 1 proton, right? That's the definition. It has 1 proton, that never changes. So here you see the 1 proton in the nucleus. So 2 equals 1 proton plus, it's really easy math, right? 1 plus blank equals 2. 1 plus 1 equals 2. So that means there must be 1 neutron. And that's what you see here in the middle, 1 proton and 1 neutron. That gives us the mass of 2. And then still you see your 1 electron floating around because protons and electrons are going to cancel each other out. Now, if you keep collecting hydrogen, even more rare, you might find hydrogen with a mass number of 3, even heavier. So it's still hydrogen, so it still has 1 proton, right? Here in the nucleus, you see it's 1 proton. But remember, mass is protons plus neutrons. If the total mass is 3, 3 equals 1 plus 2. There must be 2 neutrons. And that's what you see here in the nucleus, the 2 neutrons, to give you a total mass of 3. You still only have 1 proton, right? 1 positive charge, so you still only have 1 electron out there orbiting in the electron cloud. This slide and the next slide are just showing you different elements that are present in the human body. The periodic table of the elements is pretty expansive. Most elements are not found in the human body. The human body has a few core elements that make up most of our components. So oxygen, carbon, hydrogen, and nitrogen make up most of the human body. These are relatively small atoms. We don't have very many big atoms present in our body. then we have, calcium, phosphorus in our bones, for example, potassium, and then here you see sodium, chloride, magnesium, sulfur, iron, iodine, present in the body in lesser and lesser and lesser amounts. You don't need to memorize anything from that. That's just kind of FYI. Okay, so you know that our body is made out of atoms, right? Millions of atoms, and that those atoms join together to form bigger things, and that's how we build our body, right? That's how we build fats, or water, or proteins, or sugars, etc. We know that atoms are made out of protons, neutrons, and electrons. We know that the number of protons never changes. We know that the number of neutrons can be different in the different isotopes, right, or the different versions of the element, but that's not something that we're going to see, changing or flipping back and forth. The thing that we do see changing in atoms is the electrons. So we're going to talk about electrons for quite a bit because electrons are very important in determining how an element behaves. So like, what does it do? When you put two atoms together, do they join and build something bigger? Do they push away from each other? Like what happens when you put two atoms together is based on its electrons. So the electrons in the electron cloud determine the reactivity of an element. Again, reactivity is just like behavior, right? It's going to tell us what that atom is going to do. How is it going to behave? Okay, so now when we look at the electrons, remember the electrons are moving around really fast in the electron cloud, right? This kind of area around the outside of the atom. Now, this electron cloud has electron shells or energy levels in it. So the electrons aren't all just, thrown in one bunch. There are different levels that go out from the nucleus, and each level holds a maximum number of electrons. Again, most atoms in humans are pretty small. So in humans, most of our atoms have only up to the first 4 shells. Really, the first 3 shells are most common in humans. So again, bear with me. So those electrons exist in shells, right? Or you can think of them kind of like floors, right? And each floor holds a maximum number of electrons. Now, atoms have the minimum number of shells needed to hold their electrons, right? So what I mean by this is there are no empty shells. So if an atom has 1 electron, it's only going to have 1 shell, right? It's not going to have empty shells. It only has the number of shells that it needs. Now, when we look at the number of electrons in each shell, for our purposes, the first shell can hold 2 electrons. The second shell can hold up to 8 electrons. And again, we're only going to go to 3. The third shell can also hold up to 8 electrons. Okay, now these shells fill in order. Okay, the lower shell fills first. So the first shell is going to fill up with electrons. If the atom still has more electrons, then it'll build out to the second shell and it'll put electrons in that shell. If that fills up, then it'll build out to the next shell and it'll put electrons in that shell. Whatever the outermost shell is, it doesn't matter, it could be the first, the second, the third, fifth, whatever the outermost shell is in that specific atom, we call that the valence shell. That's the shell that determines the behavior of the atom, right? That's the shell, the electrons in this valence shell are what determine the chemical bonding of the element or the behavior of the element, okay, what it's going to do when you put it together with other atoms. We're going to go through multiple examples, just kind of roll with me for now. So here we see two different elements. Here on the left, this is showing us like a drawing of an atom of hydrogen. So this is one atom of hydrogen. Hydrogen, what we're going to do is we're going to map out the protons, neutrons, and electrons, okay, for each of these. Hydrogen is atomic number 1, and remember that tells us the number of protons that it has. So protons, neutrons, and electrons. It's atomic number 1, so that means 1 proton. Remember, at the start, before the atom has done anything, it's going to be neutral. So protons and electrons are going to cancel each other out. So 1 proton means it must also have 1 electron. Okay, positive proton, negative electron means it's neutral overall. Now, to find the number of neutrons, remember we need to look at the mass of the atom. The mass of this hydrogen is 1. Okay, remember mass equals protons plus neutrons. If the mass is 1 and we have 1 proton, that means we must have 0 neutrons. So when I draw this hydrogen, I'm going to put my protons and neutrons, which I don't have, in the middle. So in the nucleus, I have my 1 proton, and now I'm going to do my 1 electron. Now remember, the electrons go in the energy shells. We fill the first shell first. So here I've drawn 1 shell, and we said the first shell can hold up to 2 electrons. So I'm going to put my 1 electron in that, and that's it. Now that shell is this atom's valence shell. That's its outermost shell. Okay? It has 1 out of a possible 2 electrons in its valence shell. Now this second one over here, this is showing us helium. Helium is atomic number 2, and helium has this helium has a mass number of 4. So let's go ahead and map everything out. Let's put everything we learned together. We want to know how many protons, how many neutrons, and how many electrons. And then we're going to place those electrons in their appropriate shell. So atomic number 2 tells us it has 2 protons, okay, 2 positively charged protons here in the nucleus. Now, remember, positives are going to cancel out the negatives. So if it has 2 positively charged protons, it also is going to have 2 negatively charged electrons. And then to find neutrons, we have to look at the mass. Okay, the mass is 4. 4 equals protons plus neutrons. We have 2 protons, so that means we must also have 2 neutrons. So let's put our 2 protons, 2 neutrons, and 2 electrons in this atom. The protons are in the nucleus, the neutrons are in the nucleus, the electrons are going to be orbiting around in the electron cloud. I have 2 electrons. Remember, I can put 2 in the first shell. So I draw my first energy shell. Both electrons are there. That's it. That means this shell, this first shell, is my valence shell, right? We don't have empty shells. So both electrons fit in that first shell. That's my outermost shell. That means that my valence shell is full. Okay, the outermost shell is full of electrons. In a little bit, we're going to learn that's what an atom wants. All of this building of bigger things and reactions and everything that happens with chemicals is to try and fill that valence shell. So helium is very stable. It doesn't react with other stuff. It is happy on its own because its valence shell is already full. I'm kind of getting ahead of myself, but all right, let's see 2 more. Okay, here on the left, I have lithium. Lithium is atomic number 3, and it has a mass number of 6. I cannot see that, it's really small, but I'm thinking I remember correctly, it's 6. So first off, let's figure out protons, neutrons, and electrons. And again, you should be able to do this. Everything I'm doing right now, you should be able to do by the end of this, okay? If I tell you the atomic number and the mass, you should be able to tell me the number of protons, neutrons, and electrons, and you should be able to put those electrons in the right shell. So atomic number 3 tells me I have 3 protons, and remember to start 3 electrons. Now to figure out neutrons, I need to look at the mass number. Okay, the mass is 6. 6 equals protons plus neutrons. So 6 equals 3 plus 3. That means I also have 3 neutrons. Now let's put our protons, neutrons, and electrons in the atom. Remember, the protons go in the nucleus, the neutrons go in the nucleus, then these 3 electrons I need to put in my electron cloud. The first shell, remember, only holds 2 electrons. So here I have my first shell, like the first floor, and I filled it up, right, with 2 electrons. I still have 1 more electron to place. So that means that this atom has to have a higher energy level shell. So here is this second shell, and we put our 1 electron in it. Remember, this second shell can actually hold 8 electrons. So this lithium has 1 out of 8 in that shell. Okay, that second shell is the valence shell. Okay, that's its outermost shell. Filling these shells, I kind of think of it like a hotel, right? Like people come into the hotel and you're going to put them on the first floor. Once the first floor is filled up, then you start putting them on the second floor, right? Once the second floor fills up, then you put them out on the third floor. Kind of like that idea. That's just how I've always pictured it. Okay. Last example that we'll go through, and then we'll talk about bonds and like how we can manipulate these electrons. So this is neon. Hey, neon is atomic number 10, and it has a mass number of 20. So I'm gonna I want you guys to pause for a second. Okay, go ahead, pause your video, and I want you to do it. Figure out protons, neutrons, and electrons, and draw it out. And then press play and see if you were correct. Okay, if not, rewind and start this part over. Okay, so atomic number 10 tells you that you have 10 protons and you're starting with 10 electrons. Right? Protons and electrons, positives and negatives, cancel each other out to have our neutral starting place. In order to find neutrons, we need to look at the mass. The mass number was 20, so 20 equals protons plus neutrons. 20 equals, I know I have 10 protons, so 10 plus 10. Very frequently, you guys, the number's the same here. Like you saw 3, 3, 3, right? 10, 10, 10, but not always. So don't just assume, always look at your mass number because it might not be the same. Okay, so our protons are in the nucleus of the atom. Our neutrons are in the nucleus of the atom. Now we have our 10 electrons that we need to place. How many go in the first shell? 2. So 2 electrons are in our first shell. Then we have our second shell. We had 10 electrons. We placed 2, so we have 8 more to place. How many can we fit in the second shell? 8. So here you see 1, 2, 3, 4, 5, 6, 7, 8. We've put all 8 in that second shell. Now we're done, right? That's what neon looks like. This second shell is our valence shell. That's the outermost shell. And we happen to have a full valence shell. We have 8 out of a possible 8 in that valence shell. So neon, like helium, is also very stable because it's happy. It already has what it wants. It's completely filled up its shell. Okay. Again, think of a hotel. You want to fill up your rooms, right? You want every single room full so that you're getting your maximum benefit. All right, so in the beginning of the lecture, I said that the way we build our body, right? The way we build big, tangible things that you can see and touch is because atoms join together to build bigger chemicals, right? Bigger compounds and molecules. The way that atoms join together to build something bigger is with a chemical bond. So two atoms form a bond between them, and then instead of having two separate things, you have one larger thing, right? One larger molecule. And that continues with more atoms and more and more and more and more until you have something very large. Now, a chemical bond is actually occurring because of the electrons in the valence shell of the atom. Okay, so bonds exist because of the electrons, and we're looking specifically at the electrons in the valence shell, the outermost shell. Now, a chemical bond happens because we can share these electrons. You can have two atoms that come together and decide to share electrons with each other. Or you can have two atoms that come together and either take an electron, right, gain an electron, or they lose an electron, right, they give one away. So there's multiple different things that atoms can do with these electrons, but they do something. They either share, gain, or lose electrons from their valence shell, and that forms a bond between two atoms that holds them together. Now, again, the reason the atoms are doing this, the overall point, is that they want a full valence shell. Okay, the valence shell is the outer shell. That can be the first shell, it can be the second, it can be the third, it doesn't matter, depending on how big the atom is. Whatever that specific atom's outer shell is, the atom wants it to be full. Okay, just like we saw, neon already has a full valence shell. So it doesn't need to react with anything. It doesn't need to form a bond with anything. It's already happy, okay? So it's very stable. So the major types of chemical bonds that we're going to talk about are ionic bonds, covalent bonds, which there are actually two types of covalent bonds that we're going to look at, and then hydrogen bonds. These definitions that you see here, this is just a very brief introduction. I'm going to talk through all the details with you guys as we finish out the lecture. So first, an ionic bond. An ionic bond occurs when there's an attraction between two ions. Okay? An ion is just a charged atom. So you have two atoms that have a charge. They're no longer neutral. They have a charge, and they're held together with those charges. So this happens when there's an attraction between a cation, which is an atom that's positively charged, and an anion, which is an atom that has a negative charge. Now, this cation is positively charged because it gave away an electron. The anion is negatively charged because it accepted an electron. Then again, we have an atom that's positive and an atom that's negative, and the opposite charges attract, and they're held together. The two atoms are held together like magnets. Covalent bonds are very strong bonds that exist when you have two atoms that share electrons with each other. And then hydrogen, again, there are two types of covalent bonds. We can have a polar covalent bond and a non-polar covalent bond, which we will talk about. And then finally, hydrogen bonds. Hydrogen bonds are weaker bonds that exist between two polar molecules. Hydrogen bonds are also because of the attraction between a positive and a negative, but it's not a positive and negative atom. It's an attraction between a positive part of a molecule and a negative part of a molecule. Again, we're going to talk through all these details. Briefly, when chemical bonds join atoms together, we don't have an atom anymore, right? An atom, remember, is one single unit, one hydrogen, one oxygen. Once they form a bond and join together, they're no longer atoms. Now what we formed is something larger. We have formed a molecule or a compound. And these two terms are used interchangeably very frequently, but technically the definition between them is different. A molecule is when you have two or more atoms joined together with strong bonds. For our purposes, you guys, I'm not worried about the strong bonds, the strong or weak bonds. I'm more worried about this first part. So a molecule is when you have two or more atoms joined together. It doesn't matter what kind of atom, right? It doesn't just, they could be any kind of atom. They could be the same kind of atom. Just two or more atoms joined together gives you a molecule. With a compound, it's two or more atoms of different elements. So you have to have at least two different elements in order for it to be a compound. Based on this, compounds are all classified as molecules, but not all molecules are compounds, okay? Because a compound is a more complex definition. So for example, H2, that means you have two hydrogen, okay? Two hydrogen atoms joined together. That would be a molecule, right? Two atoms joined together, that's a molecule, but that is not a compound because I only have hydrogen. I don't have two different elements present. H2O, right? Water. That means two hydrogen atoms and one oxygen atom. So I've got three atoms all joined together. That's a molecule. Yeah, I've got two or more atoms. And that's a compound. Okay, so H2O is a molecule and a compound. Two or more atoms, and I have at least two elements. I've got hydrogen and I've got oxygen. Okay, so molecule and compound. Okay, so now we're going to spend a decent amount of time talking through these different types of bonds. And it's very important that you understand, this part, that you understand what it means to be, positively charged, or what it means to be negatively charged, what it means to be polar or non-polar, because these concepts are going to carry through all the way through A&P1 and all the way through A&P2. So if you've gotten to this point of the lecture and you're still not quite sure about, electrons or protons or what positive is, what negative is, I recommend you rewatch it, right? You really want to understand everything in here. It might seem like it has nothing to do with the human body, but these concepts are going to be key as you move forward. So first, we're going to talk about an ionic bond. An ionic bond is just a bond between two ions. An ion is a charged atom. Remember, we said when we first start with an atom, it is neutral. It has no charge because the number of protons is the same as the number of electrons. Protons are positive, electrons are negative. If they have the same number of each, they cancel each other out, and it's neutral. If that atom does not have the same number of protons and electrons, then it's not neutral anymore, and it's going to have a charge. That is called an ion. So once the atom has a charge, it's now an ion. Now, we said that the atom, the reason it's charged is because it does not have the same number of protons and electrons anymore, right? So let's say I'm starting with lithium, right? Lithium, remember, has 3 protons and 3 electrons, so it's neutral. Now, if lithium was going to become an ion, if it was going to be charged, that would mean that these couldn't balance anymore, right? We couldn't have the same number of protons and electrons. So just really quick, think about this for me. Which one do you think changes? Does the number of protons change, or does the number of electrons change? Hopefully you said the number of electrons changes, because the number of protons never changes, right? Remember that this lithium is defined by its number of protons. The number of protons is 3, period. So it's going to have 3 positive charges no matter what. the number of electrons can change. Remember, it can give away electrons, it can take electrons, it can share electrons. We can change the number of electrons. So say, for example, lithium were to give away an electron, and now it only has 2 electrons. Well, now remember, the charge is protons minus electrons. So if it has 3 protons minus 2 electrons, that equals +1. So that means overall that lithium would now have a positive charge, right? Because it gave away its electrons. It gave away negative charges. Okay, that's the gist of what we see happening with ions. Okay, how an ion is formed by giving away electrons or taking electrons so that protons and electrons are no longer balanced. So with an ionic bond, again, it's a bond between 2 ions, a bond between 2 charged atoms. One atom is the electron donor. It's the one who's giving away electrons. Okay, that atom loses 1 or more electrons and becomes a cation. Okay, just like we saw with the lithium, gave away an electron, became a cation. Cations have a positive charge. The other atom is the electron acceptor. He gains those electrons and becomes an anion. An anion is an atom that has a negative charge. Okay, so 2 atoms, one of them gives his electrons, 1 electron, 2 electrons to the other atom. So now they both have changed their number of electrons. One has given away electrons and become positive. The other one has taken those electrons and became negative. So now I have 2 ions, cation and an anion. They're opposite charges. Opposites attract. Okay, not just in dating, in chemistry as well. Opposites attract. So positive charge and negative charge, they're held together exactly like a magnet. Okay, that's what magnets are. We pull all the electrons to one side so that there's a positive pull and a negative pull. So opposites attract. Now those 2 atoms are held together with an ionic bond. The way I remember cation and anion, like which one's positive and which one's negative, is go ahead and write the word cation. C-A-T-I-O-N. It has a big positive right in the middle. Okay, cation has the positive written right in the middle of it. So cations have a positive charge. Okay, so we're going to take a second to look at the formation of an ionic bond. And this is going to really take together all of the principles that we've learned so far as mapping out our electrons, figuring out the number of protons and electrons and all of that. And then finally it culminates with forming the bond. So we're looking at how we form an ionic bond between sodium and chlorine. This eventually is going to give us sodium chloride, which is table salt. First off, in this first part, we see our sodium atom and our chlorine atom. This is how they exist before, anything has happened to them at all. This is how they are naturally. So first off, let's look at sodium. Okay, sodium here is atomic number 11. So remember, that tells us that it has 11 protons, which are positive, and it has 11 electrons, which are negative. So let's go ahead and place those 11 electrons. Right, we have our sodium. The first shell holds 2. So these 2 yellow dots are showing you the 2 electrons. The second shell holds 8. So we see these 8 little yellow dots. Now that's a total of 10. We still have 1 more electron to place. So sodium has to have a whole nother shell. It has to have that third shell to place that 1 more electron. So that's what you see. Sodium has this third shell with 1 lonely electron. Remember, it can hold up to 8. So sodium's not very happy. It only has 1 out of 8 electrons. And remember, the goal is to fill that valence shell with electrons. Now, sodium could try to take 7 electrons, but that's going to be really hard. It's much easier to give away 1, because remember, the atom does not have empty shells. So if sodium gives this one little lonely electron away, this third shell disappears, and now all of a sudden the sodium is left with that full second shell as its valence shell. And that's exactly what happens. Sodium gives away that 1 electron, and then if you look here at this second picture, this is the sodium ion that forms. Now that third shell has gone away. The valence shell is now the second shell, and it has 8 electrons, which means it's full. So the sodium is now stable. He's now happy. But it's now a cation. It now has a positive charge, and that's why you see this little positive right here. That's representing the positive 1 charge. Because, remember, for charge, it's protons minus electrons. Our sodium still has 11 protons. That doesn't change. But now, instead of subtracting 11 electrons, it's only 10. It gave 1 away. So 11 minus 10 equals 1. Okay, plus 1. If there's just the plus sign, we just assume it's a 1. If it was a plus 2 charge, we would actually write the 2. But if there's no number and it's just a plus or just a minus, we just assume it's 1, plus 1, negative 1, etc. All right, so that's how we form our sodium ion. Now let's look at chlorine. Chlorine, which you see down here at the bottom, is atomic number 17. So it has 17 positively charged protons and 17 negatively charged electrons. Let's go ahead and place those 17 electrons. How many go in the first shell? 2, right? You can see that. 1, 2. How many go in the second shell? 8. So you can see this, the second shell there has the 8 electrons. So that's 10. There's 7 left. So we have our third shell, and we put 7 electrons in that third shell. Remember, it can hold 8. So just like sodium really wanted to give away 1 electron, chlorine really wants to take 1 electron. So they're perfect for each other. Chlorine has 7 out of 8. He's so close to having a full valence shell. He just needs 1 more electron. Okay, so again, the sodium is the perfect partner for the chlorine. So that 1 electron that sodium gave away, that's going to come over here and fill up the valence shell of chlorine. And that's what you see happening. If you look at this second picture, now we have a chloride ion, right? It's still has its 17 protons in the nucleus, still has its neutrons, none of that's changed. The only thing that's changed is it has gained an extra electron. So now instead of 17 electrons, it has 18 electrons. If we were going to calculate the charge, remember it's protons minus electrons. So 17 protons minus 18 electrons. 17 minus 18 is negative 1. So that's why you see this negative sign here, right? That's saying that the chloride ion has a negative 1 charge. It is now an anion. So we have a positively charged cation and a negatively charged anion, and they are attracted to each other just like magnets are attracted to each other. Okay, so like the opposite poles of the magnet. They are held together with that attraction, and we call this sodium chloride. Okay, table salt. 2 ions attracted to each other because of their opposite charges. All right, that's an ionic bond. Covalent bonds occur when instead of atoms giving away electrons or taking electrons, you have 2 atoms who come together and agree to share pairs of electrons. So they overlap their shells and they'll share pairs. They can share 1 pair of electrons, 2 pairs of electrons, 3 pairs of electrons rarely. When 2 atoms come together and share pairs of electrons, each atom donates 1 electron to the pair. Okay, so if they're sharing one pair of electrons, each guy gives one electron to the pair and then they share them. Sharing one pair of electrons is called a single covalent bond. That's represented by drawing one line between them. So like C, one line, C. That means you have two carbon atoms sharing one pair of electrons. Sharing two pairs of electrons is a double covalent bond. So you would draw two lines. So like C, two lines C. That's sharing two pairs. So 4 electrons. Sharing 3 pairs is a triple covalent bond. That's 3 lines. We don't really see that very often in humans. Okay, so here we'll talk through just the first couple examples. We don't need to get too complicated with it. I'm not going to talk about the second two, but this shows you the way that this happens. So first off, let's look at hydrogen. Okay, you see 2 hydrogen atoms, right? There's a line between them, so they're sharing one pair of electrons. So this is a molecule of hydrogen. They're held together with a covalent bond. Now, each hydrogen, remember hydrogen's atomic number 1, so each hydrogen has 1 electron. So I have a hydrogen over here, and he has 1 electron in his shell. And then I have another hydrogen here, and he has 1 electron in his shell. Remember that that first shell can hold 2 electrons. So both of them really want 1 more electron. But when they come together, they can't agree on who should get it, right? This guy's saying, no, you give me yours. No, you give me yours, right? And neither one wants to give up all of its electrons. So instead, they come together and they agree to share. And that's what you see here. Their shells overlap with each other. Each gives 1 electron to the pair. And these electrons are moving, right? They're really rapidly moving everywhere, really, really fast. So both of them have access to 2 electrons in that shell. So they're both happy. We didn't add any electrons to the mix, so the charge doesn't change. We didn't take any electrons away, so the charge doesn't change. There's no charge, there's no number of electrons that's changing here. They're just sharing the pair of electrons. So for each of these, there's 2 electrons in this shell. The shell is full, they're stable and happy. Sometimes, again, sharing 1 pair of electrons doesn't give you enough. Sometimes you have to share 2 pairs of electrons. And that's a double covalent bond. That's what's happening here with these 2 oxygen atoms that are being held together. I'm not super worried about you being able to like put together complex models of this. Just understand that a covalent bond occurs when 2 atoms overlap their shells and they share pairs of electrons. What's more important is for you to understand the 2 types of covalent bonds. So there are non-polar covalent bonds and there are polar covalent bonds. In both, it's covalent, right? So in both types, you have 2 atoms coming together, sharing a pair of electrons. It's just when they share those pairs of electrons, they can share them evenly or unevenly. A non-polar covalent bond is when you have equal sharing of electrons. This happens when you have 2 atoms that are of the same element, like the hydrogen. 2 hydrogens sharing a pair of electrons, they're going to share them equally. They're the same size, they pull on the electrons with the same strength, it's going to be equal. So this forms a balanced molecule with no charges at all. Right? For example, H2, okay, 2 hydrogen atoms coming together, sharing electrons. O2, right, 2 oxygen atoms. Think of 2 people playing tug of war, right? If you have two people that are the exact same size and the exact same strength, the rope's not going to pull to either side. They're going to be even. It's going to be balanced and in the middle. Okay, that's a non-polar covalent bond. When the atoms come together and form a molecule, it forms a non-polar molecule, okay, a balanced molecule. Polar covalent bonds occur when the two atoms are not the same. When there's a big difference between them. So there's unequal sharing of electrons. You guys, I don't mean to say like anytime they're not the same, it's polar, because that's not true. You could have a big long chain of carbon with like hydrogen coming off of it everywhere. That's perfectly balanced and perfectly nonpolar. Okay, so it is possible to have a bond between two different elements that's still nonpolar. But with a polar covalent bond, again, with a polar covalent bond, there is unequal sharing of electrons. So you have two atoms sharing a pair of electrons, and one of those atoms is big and strong, and he really pulls on those electrons hard. So those electrons spend way more time with that atom than they do with the other. Right? So that creates a molecule that's not balanced any longer because those electrons are negative. So those negative charges spend way more time over here and not very much over here. So now this part of the molecule is more negatively charged and this part is more positively charged. So there are two poles, right? Like North Pole, South Pole. Well, in this case, positive pole, negative pole. Okay, that creates a polar molecule. The classic example of a polar molecule is water. Okay, H2O, which you see pictured here. H2O is a polar molecule, and it's really important that you understand this. Okay, is a polar molecule. It is not a balanced molecule. It has partial charges. Now keep in mind, this is not an ion. It's not a full charge where you have one atom that completely takes an electron and one atom that completely gives an electron away. It's not that. They're sharing the pair of electrons. It's just that the electrons spend more time in one area than the other. So there's a partial charge. Okay, so let's look at water. Water is H2O, so 2 hydrogen and 1 oxygen. If you look here, this red one is the oxygen. Oxygen has 6 out of 8 electrons in its second shell, so it needs 2 more electrons. Each of these hydrogen needs 1 electron. So what happens is the hydrogen comes over here and shares a pair of electrons with the oxygen. Now the hydrogen has 2, right? If you look right here, now the hydrogen has 2 electrons in that shell. He's happy in his first shell. Now that means the oxygen has 7 out of 8, still needs 1 more. That's where the other hydrogen comes in, right? Here's this other hydrogen is coming in and he shares a pair of electrons. Now that hydrogen is happy. He's got 2 electrons in that first shell. And now the oxygen has the full 8 that it needs in that second shell. So he's happy as well. So we have 2 covalent bonds, right? There's a covalent bond with the oxygen and this hydrogen, and there's another covalent bond between the oxygen and the other hydrogen. So we've got electrons being shared, right, in both cases. Now, remember, these electrons are moving, right? They're constantly orbiting all around. This oxygen is much bigger and stronger and pulls on those electrons for more time. So these electrons spend more time over here with the oxygen than they do over with the hydrogen. So the negative charges are spending more time over here than they are over in these blue areas by hydrogen. That means that the oxygen side of the atom is partially negative. and the hydrogen sides of the atom are partially positive. Because remember, each of these hydrogen has a positive proton in the middle, and you need those electrons to cancel it out. But if the electrons don't spend very much time over there, you sense the positivity more than you do those electrons, right? So water is polar. It has a negative pole and it has positive poles. It's a polar molecule, not a balanced molecule. Now, again, that's going to be really important to understanding the way a lot of stuff behaves in the body, because the body is mostly water. Now, this next type of bond exists because of polar molecules, because of water and the way it behaves. And this last type of bond that we'll talk about is the hydrogen bond. Hydrogen bonds are not bonds between atoms. So we're not building molecules or building compounds. We're not joining atoms together. What a hydrogen bond is it's just it's a weak bond. It's an attraction between polar molecules. So again, we're not joining atoms together. This is just an attraction between two molecules, between like two water molecules, for example. Remember, opposites attract, right? Positives and negatives are attracted to each other. Well, if I have two polar molecules, remember there's a slightly positive part of the molecule and a slightly negative part of the molecule. Well, the molecules will arrange themselves so that the positive of one is by the negative of the other, and there's a little attraction between them. So if you look here at this picture, these are showing you a bunch of water molecules. Remember, the red is where oxygen is, the blue is where hydrogen is. The electrons spend more time with oxygen, so oxygen is more negative, and the hydrogens are more positive. So these water molecules will arrange themselves, right, so that the oxygen from one is by the hydrogen from another, and there's a slight attraction between them, right? So same thing, hydrogen by the oxygen, and there's an attraction. Hydrogen by oxygen, attraction, attraction. All of these little dotted lines are showing you the attractions between the molecules. Again, it's just a partial charge, so it's not like an ionic bond where they're formally held together. It's an attraction. These hydrogen bonds, right, between the water molecules are why water behaves the way that it does. This is why things dissolve so well in water. It's why water is so good at stabilizing our body temperature. It's why water has surface tension. The hydrogen bonds between water molecules cause surface tension. It's because water is attracted to itself. So for example, if you've never done this, I want you to try it at home today. Fill up a cup to the very, very top, right? Don't overflow it, but you fill up the cup to the very top and then get down even with it, right? So you can look at it right at the side like this. And if you add water drop by drop by drop, you'll see that the water will actually rise up above the top of the glass before spilling over. It'll go up a little bit higher before actually spilling. And the reason is there's an attraction between the water molecules. They don't want to separate from each other. So even though they'll go up above the glass, there's no glass holding them together, and gravity is pulling that water down. But you can go a little bit above, and the hydrogen bonds are enough to hold the water molecules together until you add too many drops and then it does spill, because it's not that strong of a bond. But like this is why like, have you ever gotten two plastic things wet and then they feel like they're sticking together and they're hard to pull apart? That's because of the surface tension of the water. Or why like leaves float on water, or water bugs can walk on the surface of water. It's all because of surface tension. Okay, that exists because of hydrogen bonds between the water molecules. Okay, I'm gonna stop there, guys. The other video that I have goes through these last few slides. I just re-recorded the first part because you couldn't see my writing. So hopefully the writing shows up this time. Otherwise, I just wasted an hour and a half of my life. So fingers crossed you guys can see my writing on this one. If you have any questions, shoot me an email or post as a comment. Thanks.